Now that we've been through 4.1 and 4.2, where we learned how to classify and balance chemical reactions, we can move into 4.3, reaction stoichiometry, which, despite being the name of the chapter overall, is probably one of the smallest subchapters. So here we'll introduce the ideas of stoichiometry and then put them into practice in 4.4 and 4.5. So we've seen the previous video, right? First, how to balance, and then the information that a balanced chemical reaction provides. Tells us the identities, the change that's undergoing, right? The number and type, what's happening to them. So the coefficients gave us the relative numbers, the simplest ratio of these things. And what stoichiometry is all about is using these quantitative relationships between the amounts of reactants and products and turning them into conversion factors to use in dimensional analysis. That's what stoichiometry really boils down to. Okay? And it's similar to concepts that you've probably already put into play in your day-to-day life. Okay? If we think about a recipe, for example, if you have a recipe to make 8 pancakes, right, the recipe is listed on the back of the box, but you could also write it as an equation. Okay, cup of milk, or sorry, 3/4 cup of milk, a cup of mix, an egg. Those are your reactants going to 8 pancakes as the product. Okay? So maybe you're hungry, you wanted to make 16 pancakes, you know to double everything. Right? Or if you wanted to make 24 pancakes, right? Feed a household, you know you would need 3 cups of mix, 3 eggs, right? And 2¼ cup of milk, just multiplying everything by 3. So if we turn that into a conversion factor, right, we can use the same ideas in dimensional analysis. Okay? If I wanted to make 24 pancakes, I know 8 pancakes corresponds to 1 egg from my reaction, so I can set up a conversion factor to determine that I would need 3 eggs. Okay? And this right here, right, introducing that new conversion factor is really all stoichiometry is about. We're using a balanced chemical equation just like we would use a recipe, because from that balanced chemical equation, it gives us really valuable information, right? How much of one reactant we need to react with another reactant, or right, how much reactant is necessary to make a certain amount of product, keeping in mind what these coefficients represent. Okay, it's good to do with molecules, it's good to do with moles. You can use those units as well, right? Mole is the ultimate conversion. You can't do this with grams. Don't do that, right? It's not, if I have a reaction that's 1-to-1, right? It is 1 atom reacting with 1 atom, or 1 mole reacting with 1 mole. But everything has a different molar mass, so it's never 1 gram reacting with 1 gram. Okay? So keep that in mind. Right? And now we use that balanced chemical equation to derive those conversion factors, also known as stoichiometric factors in stoichiometry. Right? It's a conversion factor that you are putting together to compute whatever you're asked to do. So if I look at a reaction here, right, N2 and H2 coming together to make NH3, okay, 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of ammonia, NH3. Okay? So what conversion factors can I make? Right? I could do it with moles. I could do it with molecules. Right? Moles here, molecules over here. 2 ammonia to 3 H2. I'm just putting the the coefficient and turning it into a stoichiometric factor. That's all these numbers are introducing. Right? So 2 molecules to 3 molecules, 2 molecules to 1 molecule, 1 mole to 3 moles. However you want to put it together, depending on what you're asked to do. So if I look at example 4.8 here, how many moles of I2, iodine, right, are required to react with 0.429 moles of aluminum, given the chemical equation? Well, now I have to make a stoichiometric factor. And the first thing you always should be doing with these types of problems, always, is making sure that the reaction is balanced. Okay, so just do a quick check. 2 aluminum on each side, 6 iodine on each side, that's a balanced chemical reaction. I'm good to move forward, but always check that first, okay? Because otherwise your computation and your stoichiometric factors will be incorrect. So I'm given 0.429 moles of aluminum. I'm asked to find moles of I2. Can I relate moles of aluminum and moles of iodine? I sure can. Right? That's what stoichiometry is all about. So I pull their conversion factors, 3 moles of I2 for every 2 moles of aluminum. And so I get a final answer, right? 0.429 multiplied by 3 divided by 2 equals 0.644 moles of iodine. Let's look at another one here. Example 4.10. Now we can introduce ideas from chapter 4 and chapter 3 together, because chapter 3 we learned all about how to react between units, and chapter 4 is just relating things in a chemical reaction. Okay, so this one's a little more involved. It asks us what mass now of sodium hydroxide would be required to produce 16 grams of magnesium hydroxide. Okay, so we're asked what mass right here of sodium hydroxide would I need to make 16 grams of magnesium hydroxide, given the reaction. So the first thing that I do is I check to make sure it's balanced. Okay? And I recommend you pause the video and try and solve this problem. Check to make sure it's balanced. Okay, that's good. Now what do? Well, I only have 16 grams of magnesium hydroxide to start with. So I start with that, but stoichiometry can't relate things that are in grams. So I have to convert that from grams to moles of magnesium hydroxide by dividing by the formula mass. That is an old chapter 3 type of problem. Then when I have moles of magnesium hydroxide, I can relate it to moles of sodium hydroxide. That's the new thing from chapter 4. That's stoichiometry, knowing that it's 2 moles of NaOH for every 1 mole of magnesium hydroxide. And then once I have moles of NaOH, I can again convert that to grams by using the formula mass of sodium hydroxide. And that's all shown right here on slide 90. It's a 3-step conversion, final answer of 22 grams of sodium hydroxide. Hopefully you're able to work through and solve that problem. This is what stoichiometry is all about. That right here on slide 89 is a perfect example of a question that you would see for stoichiometry on your next exam. Yep. So those 2 examples, 4.8 and 4.10, you've got other on Sapling and in your textbook, right? Give you some ideas about what stoichiometry calculations look like. Practice is the key with these things, but it's not a whole lot that's new, right? You can change up the types of beginning and ending computational steps, right? Maybe you're asked for number of molecules and you have to use Avogadro's number, or you have to use a molarity to find a volume, right? But that's all old chapter 3 stuff. Right? The only thing new from chapter 4 is relating reactants to one another, products to one another, or reactants to products, right? By using a new stoichiometric factor. And that has to come from a balanced chemical equation. Everything that's on the outside, you already know. Using molar mass to relate grams to moles, Avogadro's number, right? Units to moles, molarity to tie into a volume. We did all that in the previous chapter. The only thing that's new right here is in the middle. Using coefficients to make stoichiometric factors to relate moles of one thing to moles of another. That is what stoichiometry is. That's the key takeaway from this section. In 4.4 and 4.5, we'll learn how to use these things in other types of applications.